K is the equilibrium constant of the law of mass action. In a balanced chemical equation, it is the ratio at equilibrium of the concentrations in molarity of the products divided by the concentration in molarity of the reactants. So products over reactants. Each concentration is raised to the given stoichiometric coefficient. We use K as Kc now because this specifies that K is expressed based in terms of concentration of molarity. This helps distinguish between the equilibrium constant with respect to partial pressures, Kp. Kp takes the same form as Kc, except that we use the gaseous atmospheric pressure in place of molarity. So we take the partial pressure of each, C, D, A, and B. Since Kp has to do with gas ideal, we can combine Kp with the ideal gas law, PV equals nRT. And we can combine this with Kc, since like I mentioned earlier, they take the same form. The combined constants gives us this equation here. R being the gas constant, 0.08206 liters atm per mole K. T being temperature in Kelvin, and delta N being the sum of the stoichiometric coefficients of the products minus the stoichiometric coefficients of the reactants. Now, on to entropy. Okay. According to the second law of thermodynamics, energy, all types of energy, is said to spread out all over the world. Entropy is the quantitative measure of that disbursement. It measures how much energy has flowed from being hindered, stopped, or being localized to being widely spread out throughout the world. It's sort of like the degree of disorder in the system. Okay, so S stands for entropy. K in this expression is Boltzmann's constant, which is the gas constant divided by Avogadro's number, which gives us 1.38 times 10 to the negative 23 J per Colt. Okay. W represents the number of similar ways to arrange the components of the system. So as W increases, entropy increases as well. Okay, so now that we're familiar with entropy, we move on to Gibbs free law. Gibbs free energy is energy associated with a chemical reaction that can be used to do work. Work being the result of the force applied to the object times the distance being displaced. For instance, if you have a pencil in front of you and you push that object through a distance, you have done work. The free energy is the sum of its enthalpy minus the product of the temperature in kelvins and the entropy of the system. So we can also write this for a reaction by adding deltas in the equation, reading as a change in enthalpy minus the product of the temperature and the change in entropy of the system. The standard state of Gibbs is the free energy of reaction at standard conditions. The concentration of all aqueous solutions are at 1 molarity and the temperature should be at 298 degrees Kelvin or 25 degrees Celsius. We write the standard form the same, but we insert degree marks to indicate standard. Now, to piece the relationship between delta G and K. Together, we have to recognize the magnitude of delta G. This tells us how far the standard state is from being equilibrium, reaching equilibrium. The smaller delta G is, the closer it is to equilibrium. And vice versa. The bigger delta G is, the further the reaction has to go to reach equilibrium.